we have a portal frame consisting of vertical load 2P and horizontal load P. It also has two vertical columns, each with a moment of mu, mu meaning ultimate moment, and a beam with moment 2 mu. So, first of all, we have to find out where plastic hinges will form. Plastic hinges will form in the weaker one, whether it be the beam or the structure, so the one that can take the least load, the one of the smaller moment. In this case, mu smaller than 2 mu happens to be in the columns. So the plastic hinges will form here at the corners B and C, but on the side of the columns. If the beam was stronger than if the beam was weaker than the columns, so it had a smaller moment, we would have had plastic hinges forming at corners B and C on the side of the beam. Yet that is not the case. So, now we are going to be drawing the beam mechanism for this structure. Let's make it purple. So, we have a fixed support, another fixed support, beam, beam, plastic hinge, and now the collapsed version of the beam. This is meant to be symmetrical, and we also have a plastic hinge here. This is in reference with the rest of the structure. And we are going to say the angle here is theta, and because it's symmetrical, it's going to be theta here as well. So this one is going to be theta plus theta, so 2 theta. The load 2P is acting here. Now, the ultimate moment, mu acting here at the plastic hinge, and 2 mu at this plastic hinge. Now, we need to calculate the external workload and the internal workload. And we must also satisfy the condition whereas the external workload is equal to the internal workload. So, to find out the external workload, we have to multiply the applied load, which in this case is 2P, by the distance and the angle displaced. The distance travelled, we know, is going to be L over 2. This one. So multiply by L over 2 and multiply by the angle displaced, which is theta. Simplified version, we write this as theta L over 2 times 2P. Cancel out the 2, so we have P L theta. Now for the internal workload, we multiply the moment at the plastic hinge by the angle displaced, and then we add them up for all the plastic hinges. So here we have mu times theta plus 2mu times 2 theta plus mu times theta. So 1 mu theta plus 4 mu theta plus 1 mu theta is going to give us 6 mu theta. 6 mu theta. Now, we can equate the external workload with the internal workload, and we have PL theta equals 6 mu theta. We can get rid of the theta because it's equal on both sides. And the collapse load PC for the vertical load is going to be 6 mu over L. Nice. Now we can draw the vertical load. The vertical load. So how would it look like? It would look like this. We know that moments are maximized at corners and midspan. So we'll have a maximum moment at midspan here and maximum moment at corners. The corners being, well, these ones. And the maximum moments on each side of the beam and the column. Now we can join them up and this is what we get. The MV means vertical moment acting here. And here we have the 2 mu, 2 ultimate moment that we said. And at the bottom we have V over 2. Now we can move on to the horizontal load. So if you remember, we had the vertical load at P acting from this side. So for the beam, it's going to look like this. And for the columns, well, let's make it in the middle. It's going to look like this. Now we can draw a sway mechanism. We know that a sway mechanism is going to form when we have 4 plastic hinges. And we already have 2, and I'll show you the rest now. So the sway mechanism is due to the horizontal load. We have plastic hinge here, which means we will also have plastic hinges acting here and here. There we have 4 plastic hinges. Vertical load P. Now, we are going to call all rotations theta. So we have 4 rotations at the 4 plastic hinges, so 4 thetas. Mu for the beam, mu for the columns, ultimate moments. Same thing, now we can calculate the external workloads and the internal workloads and satisfy the equation that these must be equal. The external workload in this case is going to be the distance 0.6 L, this one here, if you remember from the beginning of the video, and P the load and theta the rotation. So we have 0.6 P L theta. Let's leave theta last because we're going to cancel it out. And the internal workload is going to be 4 mu theta. This is because we have 1 mu theta plus 1 mu theta plus 1 mu theta plus 1 mu theta. Now, equating these, we are left with 0.6 PL theta equals 4 mu theta. Simplify the thetas. So the collapse load PC is 4 mu over 0.6 L, which further simplifies to 6.67 mu over L. Now for the last part, we are going to find the combined mechanism. So, to find the combined mechanism, we are going to have to assign a reference fibre to the portal frame. We are going to, in this case, make the reference fibre be on the inside. You could have also make it be on the outside, so like here, but let's do it on the inside this time. And we're going to assign the angles. So based on the reference fibre, if it's under tension, let's draw it here. Let's look at this corner on the inside, because if you look at this one, is it tension or compression? It's tension on the inside, so it's negative. If it was on the outside of the reference fibre, it would have been tension, so it would have been positive. So now we can do this to our portal frame for the combined mechanism. But to find the angles for the combined mechanism, first we're going to have to assign the positive and negative values to the vertical mechanism and sway mechanism. Let's use red. So, for the sway mechanism, let's assume the reference fibre on the inside. Oops, theta. Reference fibre. At this plastic hinge, the reference fibre is under compression, so negative sign. At this plastic hinge, the reference fibre looks like this, so it's under tension. At this plastic hinge, compression. At this plastic hinge, tension. Now let's do the same for the vertical load. The reference fibre is actually a dotted line to visualize. Here it's under compression, so it's negative at this plastic hinge. It's going to be the same for this plastic hinge, and for this plastic hinge it's under tension, so it's positive. Now let's move our vertical one next to our sway mechanism. So now we can draw the combined mechanism. Purple. So to do the combined mechanism, we're going to basically superpose the two mechanisms. So they both have fixed supports, plastic hinge here which forms from these ones, even though this one doesn't have them. Next it's going to look like this, the beam and the columns, and I'll explain to you why. we're going to have angle theta here, from here. We are going to have angle 2 theta here, because of this one. And we are going to have angle 2 theta at C, because we have 1 theta from the beam mechanism and 1 theta from the sway mechanism. And you look at them and you see they are both negative signs, so they don't cancel out, so they're superposed, so we have 2 thetas. Now what's happening at B? We don't have a plastic hinge anymore, and that is because they were opposite signs, the plastic hinges at B. We had a positive one and a negative one, which means they're going to cancel out, so no more plastic hinge here. We already know that we're going to have moment mu, ultimate moment, for the columns, and 2 mu from the beam. This is from the very start of our portal frame that we've been assigned with. Now, as usual, we find out the external workload, the internal workload, and equate them. The external workload in this case is going to be the sum of the 2 workloads from the portal frames of the separate ones we already have. Those were P theta L and 0.6 theta LP from the previous 2, which adds up and gives us 1.6 P theta L. Add up the 2 simplified mechanisms. And for the internal workload, we're going to have to look at this combined mechanism we have here. So we're going to have to add up mu theta from here plus 2 mu 2 theta at this plastic hinge, and mu 2 theta at this plastic hinge, which is using this mu, and another mu theta here. Well, technically the theta's here, so this one. So we have, like we said, mu theta plus 2 mu theta, 2 mu 2 theta was the angle, plus mu 2 theta plus mu theta, so 8 mu theta. Equating these, we get 1.6 P theta L equals 8 mu theta. So the collapse load is 8 mu over 1.6 L, and this simplifies to so the true collapse load is 5 mu over L. This value is smaller than the other 2 simplified ones, which means it's accurate and confirms that it's correct.